I have. Alright, welcome back to bonding video number 70. Actually, I don't know what number this is anymore. So we're going to get to this 2006 question here. The structures of glucose and cyclohexane are shown below. So as you take your time and look at this, the glaring differences is that O right there. And then we also, instead of having hydrogens, we have a couple of other substituted groups. There's a hydroxide here or there. So those are the big notices. Now I will tell you, if you had a little bit better understanding of organic chemistry, you could look at this oxygen here, for example, and see that it's incomplete. Oxygen has to have an octet. And this Lewis structure is not showing oxygen having an octet. So what it's missing, and they're trying to trick you, is those two lone pairs. Oxygen must always have 4 pairs around it. So identify the types of intermolecular forces in pure glucose. So that's the key. That is the key. So glucose is polar. You got all kind of different crazy stuff here throwing off the symmetry. And so you have the London dispersion forces, of course. It's polar, so you have dipole-dipole. And here's the one students didn't get, because it's not just spelled out. You do have OH bonds, so you can have hydrogen bonding in glucose as well. It's not going to be strong hydrogen bonding because this is a big clunky molecule that's hard to interlock, but you have some. Now, pure cyclohexane, as you look at that, if you're good spatially, you can recognize that is nonpolar, and you're only going to have LDS. Alright, part B, glucose is soluble in water, but cyclohexane is not. So this is an IMF. Okay, they're both going to be covalent molecular. So to be soluble in water, you must be polar, because water's polar. And so only glucose, or you could rephrase that, say cyclohexane is nonpolar. Part C, a little thermo. Consider the two processes represented below. We've got the liquid to gas. This is the vaporization of water. There's the enthalpy for that. Process 2, this looks like breaking water up into hydrogen and oxygen. So this is an enthalpy here. And so what they've done is they've left off the subscripts here not to give the problem away. We know that if it's liquid to gas, this is going to be a heat of vaporization. And if this is an enthalpy of a chemical reaction, this is going to be a heat of a reaction. And it is chemical. For each of the two processes, identify the types of intermolecular or intramolecular attractive forces that must be overcome. So this is something they come back to very often on the AP test to see if you understand the difference between physical and chemical properties. So for process 1, it is a physical process. Only IMFs are overcome in covalent molecular physical processes. So you have to overcome IMFs, and specifically, or primarily, it's the hydrogen bond. That's what they're going to be looking for. And then you can also say, but some dipole-dipole, and very few London dispersion. All are there, but it's primarily the hydrogen bond. And that's vaporizing. For process 2, you're actually taking water and breaking it apart. So you're having to, it's a chemical process, and you're having to overcome the covalent bonds. Good old-fashioned covalent bonds. And then number 2, indicate whether you agree or disagree. When water boils, the water molecules break apart to form hydrogen. And so that's just kind of restating part 1 here. This is false, or disagree. Boiling only overcomes IMFs. and doesn't separate or break covalent bonds. Alright, moving on to 2007. IF3, they want you to draw the Lewis structure, so since we only have one here, I'll do the math out to the side. 7 for iodine, 3 times 7 for F, 28 electrons, 14 pairs. Alright, all halogens here, so you don't have to worry about double bonds because halogens do not double bond when they're terminal. I in the middle. And then we've got 1, 2, 3. We did see LF3 earlier, and this is a homolog, so we have the same structure. So we have 11. Remember that if that's a multiple of 3, nothing kooky is going to happen. But if it's not a multiple of 3, you're going to have some leftovers. And we put those on the central atom. Alright, so there's your Lewis structure. Based on the Lewis dot structure you drew in part A, so whatever you put here, your answer in B needs to match it. Predict the molecular geometry. So 1, 2, 3, 4, 5. So this is trigonal bipyramidal, and 3 of those are bonding, so this will be seesaw. You can see they love the seesaw. In the SO2 molecule, both the bonds between sulfur and oxygen have the same length. Explain this observation, supporting your explanation by drawing in the box below. Alright, before I use the box up, I'm going to come over here and do some preliminary sketching here. So we got 6 plus 12, 18 electrons, 9 pairs. So SOO, 1, 2. And that leaves me with 7. So again, we have a leftover. And that goes there. So that takes us to 0. And once you get to 0, now you can go back and start looking at the possibility of double bonds. Sulfur here does not have an octet. It has to have at least an octet. So we are going to have to put in at least one double bond. Now, could we do it there, or should we do it here? Ah, phooey. Like this. So those are resonance structures. Or, if we do take this structure we have here, and we check the formal charge, we can see that sulfur right now has 6 minus 1, 2, 3, 4, 5. It's a plus 1. This oxygen here is 6 minus 6 is 0. And this one is minus 1. So we could actually improve this structure by adding in another double bond right there. And so if you showed your formal charge work and then went to draw this, there's a couple of ways you can explain it. So back to the question statement, it says the bonds between sulfur and oxygen are the same length. So if you draw this Lewis structure based on formal charge, well, that's a huge duh, because they're both SO double bonds. They're exactly the same. They would be the same length. But if you look back at these first structures, if you stopped here, the answer is a little bit more complicated in that you have 2 resonance structures where this oxygen alternates between being double and single bond. In reality, they kind of switch back and forth. So over time, you're going to get a bit of an average of the 2. So about 50% of this one and 50% of that one. And that makes it, if you take a huge sample and measure it, enough measurements of each to look like a 50-50. And then part D, on the basis of your Lewis structure, identify the hybridization of the sulfur atom in SO2. So again, this, whether you put double bonds or leave it over here, is not going to change your hybridization. You have 1, 2, 3 domains. Same here, 3 domains. And even if you did this one, 1, 2, 3 domains. So at the end of the day, no matter which structure you chose, you get 3 domains. So that is an s orbital, a px, and a py. So that's sp2. Trigonal planar is always sp2. All right, hit pause if you want to work 2008 by yourself. All right, so we've got here ionization energy problem. Write the equation for the ionization of atomic fluorine. All right, so this shocked me. This is one of the early years I taught AP Chem, and it shocked me that my students couldn't write this equation. So it's all about the definition of ionization. Ionization energy is to lose electrons. You're removing an electron. And so if you're writing an equation, all you do is take fluorine. It's atomic fluorine, not F2, it's atomic. And you're going to smash it. You can put the gas there if you want. It is going to take place in the gas state. And you're going to smash it with some energy. And whether you write the energy there or not is not really important. But what's important is that you get this. Ionization energy makes cations, and you are going to free up that electron. So it's a bit of an oxidation reaction. We're not exactly oxidizing because we don't have a reducing agent. We're just using energy to knock it out. But that's kind of what it looks like. And if you wanted to, you could put, forget that. All right, account for the fact that the first ionization energy is greater than that of atomic oxygen. You must discuss both. All right, well, so remember our important things are Coulomb's law, shielding, and effective nuclear charge. So for this one, fluorine has a +7 effective nuclear charge, and oxygen is only +6. According to Coulomb, energy is proportional to Q, so F has a greater ionization energy. Now there is actually more to this one that you do not have to write. This is what they're going for. But additionally, if you look at oxygen, and look at the orbital notation, this is good to discuss just because we don't have many orbital notation problems on here. Where oxygen's up. 1, 2, 3, 1, 2, 3, 4. Up, down. So for the first ionization energy of oxygen, this is the electron that's coming off. And that electron is being repelled by this one. So that makes oxygen also a little easier to ionize because this electron is being repelled by its spin partner. So you don't need that for this particular question, but if they asked a question, why does oxygen have a lower ionization, first ionization energy than nitrogen? Now that's a bit of a trend buster, and this would be the only explanation. So you need to be aware of that. All right, so C part, predict whether the first ionization energy of atomic xenon is greater than, less than, or equal to the first ionization energy of fluorine. So I've always had a very difficult time with this particular question because xenon is way down the periodic table. And so the effective nuclear charge of xenon is +8. So according to the trend, it should be a little higher. Okay? But on the periodic table, xenon is much larger. It's way down the periodic table compared to these two. So xenon is a large atom. So its valence is far away. From the nucleus. So we know from Coulomb's law that the energy is going to be inversely proportional to the distance. So even though we're increasing the effective nuclear charge, since this is such a much different distance, being so many rows below, the fact that it's a bigger atom means we're going to have a lower first ionization energy for xenon, even though it's a noble gas. And it's very hard because, I mean, you're trying to compare actual values here and say it's less, but it is. It's pretty far down. All right, moving on, because why not? Hit pause if you want to try your hand at this 2008 masterpiece. All right, we've got pyridine. This is pyridine. And we've got benzene. Pyridine is soluble in water. Benzene is not. Count for the difference. All right, so we know water is polar. And then so discuss both. Both are covalent molecular. Pyridine is polar. But benzene is nonpolar. And then this is the reason pyridine is polar. Throws off the symmetry. B part, I think we did this one in class today. Structures of the dimethyl ether and ethanol are shown below. The normal boiling point of dimethyl ether is 250 Kelvin. Ethanol is 351. Account for the difference. So both are covalent molecular. IMFs determined. Boiling point. All right, so we need to be careful here. I pointed this out. This one is obviously polar because it's asymmetric. This one at first glance looks symmetric, but it's not. It's a trick. This is still asymmetric. The geometry on this oxygen here is bent, which is polar. Both are polar with LDFs, dipole-dipole, but ethanol can hydrogen bond, and that's why it's greater. So, hydrogen bonding, usually the answer. Now, part C here, this is the one that really got students. Silicon dioxide melts at 201 Kelvin. Sorry, sulfur dioxide melts at 201 Kelvin. Silicon dioxide at 1883. So most students start jumping immediately into IMFs. This is not really an IMF totally question. The difference here is that SO2 is covalent molecular, but SiO2 is covalent network. Boom. That's the key. Now you just kind of got to explain it away. So to melt SO2, you overcome intermolecular forces, it doesn't really matter what they are. They're going to be dipole-dipoles, but that's what you're overcoming. To melt SiO2, you overcome much stronger covalent bonds, straight up covalent bonds. And that's why you get a higher melting point. A lot of students miss that one across the country. And then D part, believe it or not, was even worse. The normal boiling point of chlorine is 238. Is higher than the normal boiling point of HCl. And then it says account for the differences. So both are covalent network. IMFs determine BP. So it's all about what do you have. So with HCl, it is polar. It's going to have London dispersion, dipole-dipole, no hydrogen bonding. And then for Cl2, it's going to be nonpolar with just LDS. Alright, so things are looking pretty smooth here, but then we go back to answer our question and we go, oh, wait a minute. It says chlorine has the higher boiling point? Well, that doesn't make sense. It only has London dispersion forces. This should be the lower boiling point. But here's a situation, though, that chlorine only has LDFs, but it is very polarizable. Or more polarizable due to its larger size. And really the important thing is their number of electrons in the electron cloud. So its London dispersion forces are stronger in this case than the HCl dipole-dipole. So that does happen. And the boiling point is the proof. Not very many students got that. Will this ever end? Yes, this is the last problem. Hey! Alright, 2010. What a year. We got a bunch of stuff in the chart here. About this time, the College Board decided they want Lewis structures to be drawn with dots. And there was a rebellion amongst teachers and students about how stupid that was. So they backed off of it. So today, you may see a diagram like this, but probably not. If you do, a lone pair of dots between them just means a single bond. And let's see, is there a double? Yeah, like down here. If you see two pairs like that, it's a double bond. Draw the complete Lewis doctrine. Anyway, ethine. Draw ethine. So C2H2, also called acetylene. 2 times 4, 2 times 1, that's 10 electrons, 5 pair. Alright, so we're going to get carbon, carbon, H and H, 1, 2, 3, and there's only 2 left over. They can't go on the hydrogen, so we're going to pick one of the carbons and fill it up. So that's a kooky Lewis structure. It's not good. Carbon has to have an octet. So you're thinking, well, put one lone pair over here, so they each have 3. Not really any better. The solution here really is to put both of these there and make a triple bond. So this is the way they wanted it that year. Or like we would do it now, unquestioningly. Which of the 4 molecules contains the shortest carbon-to-carbon bond length? So that depends on if you got ethine correct or not. If you did, that is the correct answer. and it is a triple bond with greater electron density. So, Coulomb, more charge, more force, smaller distance. Alright, we've got a structure for ethanoic acid. The carbon atoms in the molecule labeled X and Y. So there we go, X and Y. Identify the geometry for each. Alright, so in this first one, carbon X, I see 1, 2, 3 domains. So we're just doing, it just says geometry, so they mean molecular. So for carbon X, this is going to be trigonal planar. And for carbon Y, 1, 2, 3, 4. It doesn't matter if they're double or triple or single. So 4 is tetrahedral. And all 4 are bonding, so tetrahedral is the answer. D part, energy is required to boil ethanol. Consider the statement as ethanol boils, energy goes into breaking the CC bonds, CH bonds, CO bonds. It's false. See, I told you they do this a lot. Boiling does not break bonds. False. Boiling only overcomes IMFs. Doesn't break bonds. Part E, identify compound from the table that is nonpolar. All right, we're looking for symmetry. The one we drew here, that looks pretty symmetrical, so that would actually be a good one. Are there more answers? Ethanol? Nah. Ethane? Yep, looks good to me. Ethane thiol? No. So you have two answers. Ethane or ethine. Ethanol is completely soluble in water. Ethane thiol is limited. Account for both. Oh, for Pete's sake. Alright, so both are covalent molecular. Both are polar. Ethane thiol has LDFs and dip-dip. Ethanol also has hydrogen bond. So we're back to that again. Ethanol can hydrogen bond, not with itself, but with water. Makes it more soluble. Ethane thiol can only dipole-dipole. And we're finished.